Hi, we're going to look into how we calculate after we have finished conducting the precipitation gravimetric analysis. So all the calculations for all gravimetric analysis is based on stoichiometry, where we have the mass relationship between the analyte and the sample that we actually weigh is established, and we calculate from there. A balanced chemical equation gives the ratios in moles of the substance consumed or produced in a reaction. Let's say we have a reaction between NaI and PbNO3 we get PbI2 and NaNO3. So we have, when we balance the equation, we have the coefficient for all the product and all the substance that is being used in the reaction. So if the mass of any of the species used or produced in a gravimetric analysis is known, the others are readily calculated. Let's look into the first examples for precipitation gravimetric analysis calculation. Let's say we have a sample of an unknown chloride after drying of 0.0984 gram, and we have the mass of silver chloride precipitate, which we get from the precipitation gravimetric analysis, which weighed 0.229 gram. And we know that 1 mole of AgCl contains 1 mole of chloride. Okay, this is based on the formulation itself. So therefore, when we want to calculate how much is the percentage of chloride in your AgCl precipitate and also in your chloride sample that you use at the earlier stage of the precipitation gravimetric analysis, these are the steps. Okay. So in this case, information which is given to us is the mass of the unknown chloride sample. So we have the mass of the unknown chloride sample, and we have the mass of our precipitate, which is AgCl precipitate. We know that 1 mole of AgCl contains 1 mole of Cl. We try to use whatever information that we have here to calculate. So the first step in knowing the percentage of chloride in our unknown chloride sample is to calculate how much mole that we have for the AgCl precipitate, and then from there we can find the mass of Cl in the precipitate. And then when we already have the mass of the Cl, we can divide it with the mass of our sample to get the percentage of chloride in unknown sample. So the first step here again, we already have the mass of AgCl, which is 0.229. When we times it with the formula mass of AgCl, this is the formula mass of AgCl. Okay, formula mass. Okay, so from this you can cancel J here, and you can get the mole of AgCl, which is this value, and then you use this value to get the mass of Cl. So this is the molar mass of Cl. Okay, so from there you can cancel mole, you get the gram of Cl. So this is how much of chloride that you get in your precipitate. So we are using the mass of the precipitate to determine how much chloride we have in the precipitate. Okay, so once we already have the mass of chloride in the precipitate, we can also calculate the mass of chloride in the sample. So this is exactly the amount of chloride and the mass of chloride in the sample as well. Because the purpose of precipitation process is to get the mass of our analyte. And in this case, our analyte is the Cl or the chloride ion. When you have get the amount of Cl, which is 0.0566 gram, you can divide it with the mass of your sample. This is the unknown chloride sample just now. Okay, so when you already divide them and turn them into percentage, you get 5757% of chloride ion in a non-chloride sample. Okay. Okay, let's move to the next slide. So this is the general formula on how you calculate the percentage of analyte in your sample. Percentage of analyte is equal to weight of your precipitate times the gravimetric factor divided by the weight of your sample, and you times it with 100%. So this is how you determine your analyte. What is gravimetric factor? Gravimetric factor is a combination of the molar ratio and formula weights used in the stoichiometric calculation. In this case, gravimetric factor equals to the substance salt divided by the substance known. Substance salt is meaning that we don't know yet what is the mass of this substance, but substance known, we already know what is the mass of the substance known. From here, we can get the mass from the ratio, molar ratio, and the formula weights. Okay, let's look at the example how you calculate using gravimetric factor. For example, if you were looking for SO3 and your precipitate was BaSO4, the gravimetric factor would be substance salt divided by the substance known. In this case, the substance salt is SO3 and the substance known is BaSO4. Meaning salt and known here is in the in the context that we know their mass. Okay, so in this case, we know the mass of our precipitate BaSO4, but we don't know the mass of our analyte, which is SO3. So we are trying to use the formula mass and molar ratio in order to calculate gravimetric factor to easily determine what is the mass of SO3. Okay, so here is the formula mass for BaSO4, 233.39. And here is the formula mass for SO3, which is at T.06. So if you divide them, you will have 0.343 as the gravimetric factor. Okay, there is only one sulfur in each term and the sulfurs are balanced. So in other words, the molar ratio between the substance salt and the substance known is 1. If you look here, there is one sulfur in SO3 and one sulfur in SO4, BaSO4. Okay, so we have a balanced term, okay, between the substance salt and the substance known. Okay, what do we mean here, a balance? When we look at this second example, we still are using gravimetric factor, which is substance salt divided by substance known. So in this case, if we have the substance salt is Ag2O and the substance known is AgCl, we can see that we have one Ag here in the substance known, but we have two Ag in the substance salt. So these are called imbalance for the gravimetric factor calculation. So to balance the silver atom, a 2 is placed in front of the substance of the lower term. So here, after you put 2 in front of AgCl, you will have Ag2O and also 2 AgCl, meaning to say that you have 2 Ag in each term. Okay, so this is the formula mass for Ag2O, the substance salt, and at the lower term here, you have formula mass for AgCl times by 2. Okay, so this is how we do it if we have imbalanced number of our items and at the top and at the bottom of our calculation for gravimetric factor. So we have here gravimetric factor 0.808. So remember just now we have two type of gravimetric factor calculation. First, if you have the same number of mole between your S here, between the upper and lower term of your gravimetric factor calculation, and another type of gravimetric calculation is when you have to add a coefficient in front of your either substance salt or substance known in order to balance the upper and lower term of the gravimetric factor calculation. Okay, let's look at calculation example. We have a certain sample of an ionic compound with a known mass, which is 0.5662 gram. It contains chloride ion and an unknown metal, which is dissolved in water and treated with excess AgNO3. Okay, so what we have here, we have the sample. Okay, we have our sample here. We have our sample 0.5662. Okay, and we also have our precipitating reagent, which is AgNO3. So when our chloride ion just now from the sample react with AgNO3, it yield AgCl precipitate. So we have some information here now. We have our mass of chloride ion with chloride sample, okay, unknown chloride ion sample. We have it 0.5662 gram. So we have mass of precipitate, okay, which is AgCl. AgCl is precipitate. Okay, we have 1.0882 gram. So what are the first things that we should do? We should find the gravimetric factor. What is the gravimetric factor? It is the substance salt divided by the substance known. So you get the gravimetric factor. This is the formula mass of the substance salt divided by the formula mass of the substance known in a balanced term, meaning to say that we have the upper and lower term balanced. Okay? Now, we look at the solution for this. So you have the molar masses of Cl and AgCl. In this case, you are looking for Cl, the chloride ion mass. Okay, so what you want to do is you use the formula mass of Cl, which is the substance salt, divided by the formula mass of AgCl, which is the substance known. In this case, we have the same number of Cl on the upper term and the lower term. Okay, so we don't have to add any number or any coefficient in front of Cl or in front of AgCl because they are already balanced. Okay, so from here, you can calculate the gravimetric factor, which is 0.2472. So in this solution, we convert it to 100%, but actually we can straight away use 0.2472 in order to calculate the mass of Cl in your sample. So it's easy. You already have your gravimetric factor, which is 0.2472. You times it with the mass of your precipitate. Okay, so you get 0.2690 gram. So the aim here is for you to get the mass of Cl. It doesn't matter whether you have the Cl in your precipitate or in your sample, the mass is the same, because the mass of analyte that we get in the precipitate refers to the mass of Cl that we get in the sample. Okay, it's the same mass of Cl in the sample and mass of the Cl in the precipitate is the same thing. Okay, it reveals the same number. Okay, so how to calculate the percentage? You take mass of Cl in the sample and you take the mass of your sample times 100%, so you get the mass of Cl in the sample 47.51. Okay, note that you may have the same mass of your Cl in your precipitate and in your sample, but you will have different percentage of Cl in your precipitate and in your sample. Okay, because they are divided to the different mass. Okay, you have different mass of sample and different mass of precipitate. But what matters is the mass of your analyte in your precipitate is the same as the mass of your analyte in your sample. Let's take a look at another example. We have a 0.322 gram of sample of an ionic compound containing bromide ion, which can be dissolved in water and treated with excess AgNO3. So we get the mass of AgBr precipitate that forms, which is 0.6964. So what is the percent by mass of Br in the original sample? So this question is quite the same, because when we do precipitation gravimetry, the trend of the calculation is also the same, okay? Because it has the same step, okay? All right, now you have two information, mass of your sample and mass of your precipitate. But what you want to do is, what you want to calculate is the mass of Br in the original compound. Okay, let's look at the solution here. The molar masses of Br and AgBr are this one. So when you do the calculation, you have to take into account whether the upper term and the lower term is already balanced or not. And in this case, you have it balanced because Ag and Br, 1 mole of Ag reacts to 1 mole in AgBr, you have 1 mole of Ag and 1 mole of Br. So at the upper term, you have only Br, which is the analyte that you are looking for. So they are now balanced. You don't have to add any coefficient in front of the upper or the lower term. So after you calculate the gravimetric factor, again, the formula mass of Br divided by the formula mass of AgBr. So you get 0.4255, which is the gravimetric factor. So when you want to get the mass of your Br in sample, you have to times your gravimetric factor with the mass of your precipitate. Okay, why? Because the mass of Br in your precipitate is the same with the mass of Br in your sample. Okay, because the precipitate is taking all the Br in your sample. So this is the mass that you get for Br in your sample. So you take this mass divided by the mass of your sample times 100%. Okay, so you know that This is the percentage of BR in your sample. Okay. Again, note that you may be having the same mass of BR in your precipitate and in your sample, but you will going to have different percentage of BR in the precipitate and in the sample. Okay, so remember when you want to calculate the percentage of your analyte in your sample, you have to divide the mass of your analyte to the mass of your sample, not your precipitate. Okay, now we move to another section of our uh, lecture for LU3, which is gravimetric analysis. This is about precipitation equilibria. When substance has limited solubility, or we call it insoluble compounds, the ions of the dissolved portion exist in equilibrium with the solid material. For example, if we have a reaction of AgCl, it is in equilibrium with Ag plus and Cl. This is always a reversible situation. Okay, you have AgCl in aqueous solution, in Ag plus ion and Cl ion. So the overall equilibrium constant is known as the solubility product, or KSP. Okay, the overall equilibrium constant is known as the solubility product, KSP, for the above stepwise equilibrium. So how we do calculation for KSP? The solubility product, KSP, is equal to the solubility of Ag plus and Cl. Okay, this is the dissociation of AgCl just now into Ag plus and Cl. So you have KSP here, molarity of Ag plus and also molarity of Cl. So let's say you have here example on KSP calculation. KSP of AgCl at 25 degrees Celsius is 1 times 10 to the power of 10 to the power of negative 10. So you know here what is the KSP. Okay, you want to calculate the concentration of Ag plus and Cl negative in a saturated solution of AgCl and the molar solubility of AgCl. AgCl ionizes, so the equal amounts of Ag plus and Cl are formed when they ionize. AgCl dissociates into Ag plus and Cl negative. So you have KSP in the form of concentration of Ag plus times concentration of Cl. So let S represents the molar solubility of AgCl. Okay. Since each of the AgCl dissolves to give 1 mole of either Ag plus or Cl, we know that in AgCl we have 1 mole of AgCl, we have 1 mole of Ag plus and 1 mole of Cl. Then, if the molar solubility is represented by S, so the molar solubility of Ag plus would be the same with molar solubility of Cl. This is because 1 mole of each of these species exists in AgCl. So let's say we represent it here, KSP equals to concentration of Ag plus times concentration of Cl. So KSP equals to S times S. Okay. Let me draw something here. So let's say this is S, this is S. So this would be S, this would be S. Okay, so KSP equals to S square. Okay, you already have S square. Given in the question just now, KSP equals to 1 times 10 to the power of negative 10. So you just replace KSP in this equation. in this formula. So you get here S equal to square root of 1 times 10 to the power of negative 10. Okay, so from here you get this. Okay. All right. So the solubility of AgCl is 1 times 10 to the power of negative 5 molar. So when the product is less than Ksp, no precipitate is formed and we have a clear solution. But when the product is equal to Ksp, we have a saturated solution. And when the product exceeds the Ksp, a precipitate will form. So in this case, what do you think is happening? Either precipitation form or saturated solution, or no precipitation will form. If we look at the S that we get here is 1 times 10 to the power negative 5, which is higher compared to the Ksp. This is Ksp. So this is higher compared to the Ksp. What happened here is when the product exceeds the Ksp, a precipitate will form. Okay, precipitate will form. All right. Let's move to our next one. Let me clear this one first. All right. Now we have example for what is the solubility of PbI2 if the solubility product is 7.1 times 10 to the power of negative 9. Okay, we repeat the same calculation as we have discussed just now. We know Ksp would be the combination or the concentration of Pb2 plus times the concentration of I negative iodide ion. Okay, we know that if we represent each of the molar solubility by S, we know this would be S and this would be I. Sorry, this would, okay, this would be S square. Okay, so Ksp here is 7.1 times 10 to the power of negative 9. Okay, how do we solve this problem? If we look at here, we have Pb2 plus. So how do we go with the S? Okay, let's go to the next slide. Okay, now we have equilibrium of PbI2. When it dissociates, it's become Pb2 plus and 2I. So this is a balanced equilibrium equation. Okay, you have 1 Pb, you have 2I, and 1 Pb and 2I. Okay, so the Ksp just now is Pb2 plus times iodide square here. Okay, as has been mentioned just now. So let S represents the molar solubility of PbI2. Then you can have Pb2 plus SS and iodide ion as 2S. Why? Because you have 2I here. From the equilibrium equation, you have 1 Pb 2 plus and 2 iodide ion. Okay. You have 2 iodide, so you have this one, and you have 1 Pb, so you have this one. This goes to this, and this goes to this. Okay, so from there, you put Ksp S to S. Okay, so S here represents PB2 plus and 2S here represents 2I. Okay, and Y here you have square because you already know that this is the KSP equation. You have PB2 plus, which is here, I, which is here. So you have here square for your KSP equation. Okay, so from here, you can get the solubility, which is 1.2 times 10 to the power of negative 3 molar. Okay? Now we have another example. If the solubility of PbI2 is 1.2 times 10 to the power negative 3 molar, what is the solubility in gram per liter? So in this case, you are not going to do all this kind of calculation as we have previously discussed, but it is about the conversion of your unit from molarity to gram per liter. So how do you do it? You have molarity. Molarity equals to mole per volume because it comes from N equals to mv. Okay. So from here, you can calculate the solubility in gram per liter. Okay. You already have the formula mass here. So formula mass, okay, N equal to also mass per formula mass. So from here, you can calculate what is the N. And from here, you can do the conversion of your unit, okay? Right.